All right, guys, welcome back. Today, we are diving into one of the most fundamental and, let's be honest, one of the most frustrating parts of building any distributed system, failure detection. See, in our world, things die. That's a fact. Processes crash, networks get all clogged up, and sometimes a server just decides to take a long nap to clean up its memory. So the real question is, how do we know?
Come on, you've been there, I've been there, we've all been there. You send a request, you wait, and nothing. Just crickets. So what's the move? Is the server just having a slow day? Is the network just dropping your packets for fun? Or is that service completely, totally dead? The hard truth is, you can never really be sure.
And this, my friends, is what we call the gray area. And as our source material says, this is exactly where the nightmares for backend engineers begin. Because telling the difference between a node that's just slow and one that's actually dead, well, it's pretty much impossible.
Okay, so if we can't be 100% certain, what can we do? We have to make a guess. And our most basic, fundamental tool for making that guess is the good old timeout.
Now, a timeout isn't a guarantee that something has failed. It's not a fact. It's an educated guess. We're essentially saying, look, if I don't hear back from you in, say, 5 seconds, I have to assume you're unavailable so I can move on. It's a pragmatic choice, right? Otherwise, our own service would just hang forever waiting for a response that might never, ever come.
And this right here, this is the classic architect's dilemma. It's a trade-off with no easy answer. You set that timeout too short, super aggressive, and you'll be killing perfectly fine requests just because of a tiny network hiccup. But you set it too long, and now your users are staring at a loading spinner for 30 seconds while your system is patiently waiting for a dead process to reply. There is no magic number here. It's all about trade-offs.
You know, waiting for a user's request to fail is a really painful, reactive way to find out there's a problem. We're engineers. We want to get ahead of the problem. Can we be more proactive? You bet we can. Let's talk about pings and heartbeats.
So first up, we have the ping. Think of this as a pull model. It's super straightforward. One process, let's call it A, basically just taps another process, B, on the shoulder every so often and asks, hey, you still there? You good?
And here's the flow. It's simple. A sends out that little "Are you alive?" message and immediately starts a stopwatch. If B responds in time, awesome. A resets the watch and all is good. But if that timer runs out before a response comes in, well, A has to make a call and marks B as unavailable.
Now the other side of this coin is the heartbeat. If the ping was a pull model, the heartbeat is a push model. Here, the responsibility totally flips. Instead of being asked, process B proactively broadcasts a message every few seconds, basically shouting out to the world, hey everyone, I'm still here, I'm alive.
And this shows you how it works for the listener. Process A, it just has a timer running. Every time it hears that "I'm alive" shout from B, it resets the timer. If that timer ever runs out, A has to assume that B has kicked the bucket. Now, a really key point from the source material is you usually only do this for services that are constantly chattering with each other. If you only call a service once a day, don't waste a network bandwidth. Just handle the failure when you actually try to communicate.
Okay, these concepts are great, and they're the building blocks. But now, let's put on our system architect hats. Because pings, heartbeats, and especially timeouts, they behave totally differently when you're not in one nice, cozy data center.
Just think about it for a second. Does a 50-millisecond timeout that works perfectly between two servers sitting in the same rack, does that make any sense when those two servers are on different continents? No way!
So first, let's look at the best-case scenario, where we often start. You've got servers talking to each other inside one data center. The network is fast, it's predictable, life is good.
Your round trip time, the latency, can be as low as 1 millisecond. It's blazingly fast. In this perfect little world, an aggressive timeout doesn't just seem reasonable, it seems smart. Well, let's get real. Your application isn't just in one perfect little box. It's global. You have users and servers all over the world. So what happens when a request has to travel across the Atlantic Ocean? Well, suddenly, your baseline latency, just the time it takes for light to travel through fiber, jumps to 75 milliseconds or more. And that's before any server processing, before any network congestion. That aggressive 50-millisecond timeout you set, it will now fail every single time, even on a perfectly healthy connection.
So here's the crucial takeaway for us as architects. Your failure detection strategy cannot be one size fits all. It has to be aware of the network. This is where you see smart patterns like dynamic timeouts. Maybe you have a short one for local traffic and a much more generous one for traffic that has to cross a continent. A single static number is just a recipe for a global cascade of failures.
And all this uncertainty, all these trade-offs, it leads us to a really fundamental and honestly, a very humbling truth about building these kinds of systems.
I want you to just let that sink in for a moment. It's not that it's just hard. It's not that we don't have the right tech yet. It is mathematically impossible in the kind of asynchronous systems we all work in. Think about the two generals problem. You have two generals on two different hills. They have to coordinate an attack, but their only communication is by messenger, and that messenger might get captured. So General A sends a message, but he can't know it arrived unless he gets a confirmation back. But then General B can't know that confirmation arrived. You see? You can go back and forth forever and never get to 100% certainty. Our network packets? They're those unreliable messengers.
And because perfection is impossible, we are forced to live with two kinds of errors. You will always have false positives, where you declare a perfectly healthy node dead just because it was a little slow, and you will have slow detection, where a node is well and truly gone, but your system just hasn't figured it out yet.
So, we have to reframe our entire goal. We are not aiming for certainty. We can't have it. We are building systems that make a good enough guess about failure, just quickly enough so that the larger system can take action, like routing traffic away from a flaky node, and begin to self-heal. It is all about managing uncertainty.
And that thought leads us to our next massive challenge. We just spent this whole time establishing that we can't even be sure who is alive or dead at any given moment. So how on earth can we get a group of machines scattered all over the world to agree on the order of things, to agree on when something actually happened? That is the fundamental problem of time, and that's exactly what we're going to break down next time. I'll see you then.